Hi everyone, this is our intro to torque and rotational motion title page. So we're actually going to be at the very first page of our new unit. This is kind of just an intro looking kind of forward at some of the things that we will be learning about and hopefully giving a little clarity on where we're going throughout the rest of our units. So you need to be on wherever our title page is. It's probably somewhere around 126, but it might not be that exact page. You'll need to check. And you will probably need a ruler and you'll need something to write with, hopefully. And now I'd like you to take a minute, maybe a little more, and actually just create this table up here that I have in yellow on your page, and then fill out the linear version. Essentially, I'm asking, what is the linear version of displacement, velocity, acceleration, inertia, that just is mass, force, kinetic energy, and momentum. So take a minute and get caught up with this and fill it out. Thanks. Okay, cool. So hopefully you have filled it out and we can check our answers now together. We have X, we have V, we have A, we have M, we have F, we have K. Some notations use KE. I also might have seen K lin for linear, or maybe even K trans for translational. Translation means in a straight line as well. And then momentum, we have P. That's it. Pretty simple. Now we're going to be doing the exact same concept but with things not moving in a straight line. All of these in the past have been for things moving linearly. Maybe it's in a line up a ramp, but it's still been in a straight line more or less. Now we'll be dealing with things spinning, and so we're going to have some new symbols for the same concept. So our new version for displacement is theta. This is the Greek letter theta. It's going to be the angle you've gone through. Maybe you've gone 360 degrees. That'd be a full rotation or a revolution. We're going to use for velocity the Greek omega. It looks like a fancy W. This is omega. This is the lowercase omega. Instead of A, we have alpha. Hey, those kind of look nice and similar. It's an A. It's a fancy A. It might even look like a cute little fish. And this is alpha. Oops, I can spell. Now, instead of mass, this one gets a little strange. We have not the mass. We have how the mass is distributed. So really quickly, kind of here's just an example. I could have a solid disk and I could have a ring. They could be the same size. They could be the same thickness. They could have the same mass, but a disk, just put right here, disk. Actually, let me move this so that we're going to look maybe just up at the tip top of the page here for a moment. We can look at it right here. If we have a disk here, we'll say disk and ring. A ring is hollow, a disk is solid, but they both would have the same mass. It turns out that the disk would be easier to rotate because more of the mass is concentrated around the middle, the center of rotation, essentially. The ring is going to be harder to rotate because the mass is distributed way out here at the very end of the radius of the circle. So we're looking at how the mass is distributed. It's capital I. This is actually called the moment of inertia. Inertia is mass. Moment is kind of an inappropriate word. It makes me think of time usually, but moment just means how it is distributed in this case. Now, instead of force, we're going to be dealing with a cool new capital Greek letter. It's tau. I love writing that one. This is capital tau. When I think of tau, I actually think of like torque, or I think of the torque that a car has. That's how well it can apply a torque on the wheels to get it rotating quickly. And for kinetic energy rotating, we have K rot for rotational. No Greek letter there, just a big old K still. And now instead of linear momentum, we have L, capital L, for angular momentum. That's really it. So you'll be dealing with all these same exact concepts: displacement, velocity, acceleration, inertia, force, kinetic energy, and momentum, but now with things rotating. So you can imagine all those unit 1 equations we had, we're going to have those exact same 3 equations again. But instead of x's, we'll have thetas. Instead of v's, we'll have omegas. Instead of a's, we'll have alphas. We're even going to have Newton's second law again, F equals ma, but it will be instead torque equals I alpha, because t is, or tau is replacing F, I is replacing M, and alpha is replacing A. So you kind of see this direct connection of just swapping each of these to the new version, really. That's really all we're going to be dealing with this unit. So with that, I want to go down a little bit on our page and have you draw a circle and then kind of set it up just like this. Now you don't need to use a ruler. I made sure that my radius here is the same length as this other radius here. It'll help a little bit. If it's not perfect, it's not going to ruin anything at all, so don't worry. Okay, cool. Hopefully you're all caught up now. I want to define a new unit. That new unit is going to be what we call angles or degrees, but not actually using degrees. We're going to be measuring angle theta, this angular displacement. I'm going to start saying it. Angular displacement, that's what our theta really represents, how far we've moved in the percentage of a circle. In this new unit called radians. And those of you that are pretty mathy, you've dealt with radians, but I don't know if you really get what they are. You just know it's something you use instead of degrees. And so here is what a radian fundamentally is. You take the radius and you have it drawn as I have here. And then you draw the same radius just vertically. It's at a 90 degrees essentially. And now what I need you to do is draw the radius again. Actually, we're going to do something instead before that. You need to imagine, this is where it gets a little odd. You need to imagine right here at the end of this little radius right there, imagine taking your finger and pushing it to the left so that this blue line doesn't stay a line. It actually curves along the circle, but it still stays the length of one radius. It still is R here. It's just not in a straight line anymore. And now imagine drawing another radius to connect the first one and the second one together. Just like that. So really we have an R and an R and an R. This is some angle here. This is some angle, and that angle is 1 radian. I'm going to put rad because they're pretty rad. That's the definition of what a radian is. If you had 1 radius of the circle along the length of the circle as like an arc along it, that is what a radian is defined to be. And so what we're going to do here is to actually, well, we're going to define it. I'm going to kind of leave this stuff blank for a minute and go down to saying that theta in radians, I'm looking at this purple part now, has a triple equal sign. This triple equal sign is pretty sick. It means that it is defined to be. This is like humans have defined this. Humans have defined radians to be S over R, where S is actually the length of arc, or maybe I'll just call it the arc length. And so that's it. That's all you would do. If I went and I had twice the radius here, I'm going to trace it twice approximately. If I had it twice, well, you'd have, instead of S, you'd have 2R over R, and you'd have 2 radians. That's actually all it is, which is pretty sweet. Now it turns out that you can convert radians to degrees, and we'll do that in a moment here. But let's actually look over at this circumferency business here. It turns out that if you counted how many arc lengths of radius R, how many of these blue lines essentially it would take to go the entire circle in length, you counted how many it would be to go all the way around, it would turn out to be 2 pi, that many, 2 pi many r's. So pi is this number, it's 3.14. If you had 2 times pi, if you had that many of these little blue arc lengths stretched around it, that would cover exactly the circumference. And so if you think about how many arcs it is, we already just answered it. The number of arcs, we just said it's 2 pi. It is 2 pi many of these radii of the circle. And where this gets weird is like the radius isn't set. You could have a bigger circle or a larger circle, but the proportion there is always the same. And so I would say that one full rotation is 2 pi radians. Where radians, we're really kind of saying, is now this new unit of angular measurement that isn't degrees really. That's kind of really what we're getting at here. And so if we wanted to look at some of these angles here now, we could go ahead and say that, well, 30 degrees, I want to skip the 30 degree one for a moment here. I want to go to this 90 degree one right over here. So take a moment and hopefully you can sketch these where you already have them sketched, or pause the video here for a moment. But we have 90 degrees. 90 degrees. 90 degrees equals how many radians? Well, if it takes 2 pi many radians to go the full circle, it would take 1 pi to go half the circle. So it would take half of a pi to go to a quarter of a circle. So we're going to have pi over 2 radians. Or maybe another way that we could kind of think about this, running out of colors, I'm going to pick up a sweet orange here. We maybe just call this a quarter of a rev for a revolution. Now that we've done kind of the harder, the first one, we can look at 180 degrees. 180 degrees, well, that's double 90 degrees. That's pi many radians. Or in other words, that equals half a revolution, just 1/2 of a full revolution around the circle. Now we can go to our last one here and we can see that we obviously are going a full circle. We have 360 degrees. And we've already answered this one. This is 2 pi many radians, which means that we have 1 revolution. This is kind of an interesting way to, 3 different ways to think about the same angles that something is moving through a circle. And now we can come up and actually do this 30 degree one. We've done the 90, so 30 degrees is just going to be a third of that. So a third of pi over 2 is going to give us pi over 6. It's 1/3 of a half essentially. So you have pi over 6 radians. And this is really what a radian actually is. And this just becomes a weird kind of ratio here. We end up having a third of a fourth, so we end up getting 1/12 of a revolution. I hope that made sense. Now that we have a little space here, I want to look at just what 1 radian is, because we haven't dealt with just 1 radian. So I'm going to go, maybe I guess just down here, but we're going to really be thinking about this picture kind of up here. If we want to find that angle for it, I want to find just 1 radian. Well, 1 radian. How have we been doing these conversions so far? We've really been taking the angle and we've kind of been dividing it by 2 pi really. So if 1 radian, I want to compare that to the number of degrees around a circle to the number of radians around a circle. Really, I'm kind of doing a unit cancellation here. A full circle is 360 degrees. A full circle is 2 pi many radians. And so it turns out that 360 over 2 pi gives us 57.3 degrees. So 1 radian is 57.3 degrees, which is a really nice, awkward number when you stop to think about it. So I hope that helped with what the heck some of these how are we going to be approaching some of these? And I want to actually look and give you some conversions that will help compare these values. All of these angular things we're going to have to use this unit need to stay in radians, and so you're going to have to make sure you're not using that degree symbol on your calculator. You have to make sure it's actually in radians. And so here are some conversions that will be valuable in going from the linear version, like arc length here, arc length, to the kind of rotational version, like our theta here is kind of now our angular version of distance. And again, remember that this triple equal sign means defined to be. And so a couple other just handy conversions. If we want to look at this new omega thing's angular velocity, it looks like a fancy W. That actually is v divided by r. If you had the velocity in meters per second and you had the radius in meters, you'd end up having the angular velocity, and that would be in radians per second. We can do the exact same thing here with alpha. Alpha follows the same pattern. It's really, we have the linear thing over r gives us the angular thing. If we look at the omega one here, we have the linear velocity over r gives us the angular velocity. And so here we're going to have the linear acceleration over r gives us the angular acceleration. And maybe just one little throwback to remind you from our circular motion unit, velocity is distance over time. But since we're traveling around circles now, it is 2 pi r is going to be our distance. And our time is going to be the period, the time to go around once. So take a breath, pause the video. Hopefully that kind of makes sense thus far. And what I would like to challenge you to do is using these symbols up here. I'm going to give you some of our Unit 1 equations, and I want you to write out the, or sorry, not Unit 1, our Unit 1 and 2 and 3 and 4 and 5, all of the units so far this year together as equations. And I want you to write out the angular version of them actually. So these are our old versions here. I'm going to just pause on these two and I'll kind of start you off with a simple. This is Unit 1. I want you to write the angular version over here on the right side. So pause it, write those. And then we're going to do the exact same thing here for some of our other former equations here. And that will really be it for our video. Hopefully that makes sense. In a moment, I'll scroll over and actually give you a chance to compare to see if you did these correctly. And ta-da, there are the new versions. We're replacing V's with omegas, A's with alphas. Time is, well, T for time still. X has become thetas. Forces become taus. M's become I's. P's become L's. And I think that really sums it up. So hopefully that made sense. Have a good rest of your day.